Welcome to the Explainer. Let's just dive right in, shall we? Today, we are setting the stage to explore the invisible machinery that quite literally powers our modern world. I mean, from the exact moment you flip on a light switch in the morning to the second you take off on a runway, you are relying heavily on one seriously incredible piece of engineering.
So think about this for a second. What does a high-pitched dentist's drill, a massive commercial jet engine, and a colossal hydroelectric dam actually have in common? On the surface, obviously, they're wildly different machines doing wildly different jobs. But here's the crazy part. Underneath their exteriors, they all rely on the exact same fundamental technology. Every single one of them is powered by a turbine. Here is our roadmap for today. We'll hit 1. What is a turbine? 2. Impulse versus reaction. 3. Anatomy of a turbine. 4. Surviving extreme conditions. And 5. Designing with simulation.
All right, Section 1. What is a turbine?
At its core, a turbine is simply a machine that converts a working fluid's kinetic energy, so its velocity, and its potential energy, which is its pressure, into rotating mechanical energy. The word itself actually comes from the Latin root turbo, meaning to whirl. The best way to picture this is to think of a turbine blade acting kind of like a giant lever. That lever gets pushed by the momentum and pressure of a rushing fluid, and that force creates torque right around a central shaft. It's just a beautifully elegant through-flow approach to extracting energy. It is completely different from, say, the explosive piston-banging process of a standard internal combustion engine.
Moving on to Section 2. Impulse versus reaction.
Basically, there are two primary ways these machines extract energy from a moving fluid. First, you have impulse turbines. These guys extract energy entirely from fluid velocity and momentum. The fluid pressure actually stays completely constant throughout the whole process. A dead giveaway that you're looking at an impulse turbine is that there's no enclosing case needed to guide the fluid. Think of a classic Pelton water wheel or that ultra-fast compressed air dentist drill we mentioned. Then, compare that to reaction turbines. These extract energy fundamentally from a drop in fluid pressure, and because they rely on capturing and expanding that pressure, the flow has to be perfectly positioned by an enclosing case or shroud. Those massive wind turbines you see out on hillsides, or the incredibly complex gas turbines tucked inside commercial jet engines, those are reaction turbines.
Okay, Section 3, Anatomy of a turbine. Let's look at the actual physical machinery making this happen.
The real magic is how these core components work together in total harmony. First up, the rotor. That's the heavy wheel or drum holding the blades. And the blades themselves, they are the absolute star of the show, physically converting that fluid pressure or momentum into a directional force. But, and this is key, they don't act alone. You also have stator vanes. These are stationary, non-rotating blades sitting right upstream and downstream. They act like directors, perfectly angling and controlling the fluid's flow and velocity right before it smashes into the rotating blades. Together, a stator and a rotor form what's called a stage to completely master the fluid dynamics. Finally, the shaft takes all that raw mechanical power out of the turbine, usually running it through a gearbox to step the rotational speed and torque up or down to match whatever external machine it happens to be powering.
Section 4. Surviving extreme conditions.
Picture this. You're spinning heavy metal at tens of thousands of RPMs under unbelievable pressure. That creates a uniquely hostile physical environment. I'm talking extreme heat and friction. To survive that, you need way more than just tough metal. You need some serious advanced chemical engineering. Case in point, industrial turbine oils need a massive flash point of 250 degrees Celsius just to prevent a catastrophic failure. Seriously, if that oil degrades or ignites, the entire multi-million-dollar system literally destroys itself in a matter of seconds.
And this is exactly where specialized chemistry steps up to the plate. Take PTT Lubricants Turbine M, for example. It's an incredibly advanced oil designed specifically for water, steam, and gas turbines. It completely solves these intense thermal and friction problems using super high-quality hydro-treated base stocks. Get this, it offers over 16,000 hours of oxidation stability. It's formulated with additive tech that meets incredibly strict Mitsubishi standards for preventing sludge and varnish. And that matters a lot. Inside a turbine, even a microscopic, practically invisible layer of varnish or sludge is enough to throw a high-speed rotor totally off balance, or entirely block a hydraulic control system.
When we map out this oil's kinematic viscosity against temperature, we can see exactly why it works so well. The data clearly shows how the oil's viscosity, meaning its thickness and flow rate, behaves across massive temperature swings. And maintaining a solid viscosity index is absolutely make or break here. Whether the turbine is just starting up at 40 degrees
or running blazing hot well past 100 degrees Celsius, the oil has to maintain a stable enough viscosity to keep those moving metal parts separated. That specific thermal resistance is what extends oil drain periods and protects the super delicate high-speed bearings that hold up the entire rotor assembly.
Finally, Section 5, Designing with Simulation.
So how do we actually build these things today? Well, engineers have completely abandoned the old, wildly expensive methods of simple trial and error. Today, we design the whole shebang entirely in the digital realm first. Step 1 is flow path design, where we map out the 2D thermodynamic behavior of the fluid. Step 2 is blade and stator design. Here, engineers use mind-blowing 3D computational fluid dynamics, or CFD, to model exactly how the gas or liquid is going to wrap around every single millimeter of the blades. Step 3 is structural and thermal analysis, simulating that intense heat stress and high-frequency vibration we just talked about. And Step 4 is system design, bringing it all together to optimize the entire turbomachine. By using simulation software, like the cutting-edge tools from ANSYS, engineers can perfect the aerodynamics, the thermal resistance, and the system-wide efficiency before a single piece of metal is ever cut. It's a total game changer.
Which brings us to a really powerful, provocative thought to wrap things up today. In a world relentlessly moving toward absolute efficiency, what exactly will the turbine of tomorrow look like? I mean, we've journeyed all the way from ancient wooden water wheels slowly pushing millstones to digitally simulated, synthetically lubricated aerodynamic marvels that spin faster than the speed of sound. As our digital simulations get even smarter and our materials get even stronger, the future of engineering here is literally limitless. Thank you so much for joining me on this explainer, and hey, never stop wondering about the invisible machinery that powers our world.